Mic check, 1 2 1 2. Good evening, ladies and gentlemen. Welcome to another episode of Physics Rocks. It's true, tonight it's a year 11 topic, and we are going to look at Hooke's law and pressure. We did a little bit of Hooke's law last time, and we're going to firm that up and make sure it's all sorted out for this week. Okay, so let's get started. Hooke's law basically says that as you increase the force that's applied to some form of elastic object, that the extension increases as well. Okay, but not equally. There's some form of multiple here called K. Right, so this is what we call a proportional relationship. That force is equal to some constant times X. All right, so this F here, this is your extending force, provided the thing's sitting nice and still for you. X here is your extension. And this can be measured in a variety of units. It can be measured in meters, centimeters, or millimeters, depending on the material that you're using. And then this bit in here, which is where all the magic happens, this is called the spring constant. Spring constant. Okay, and we need to, the units for this are changeable. Alright, they can be changed. Oh, the D in there, thank you. Okay, spring constant is changeable, depends on the unit that you're using. Force is obviously in newtons, has to be, that's kind of a definition of it. Okay, so what we want to do tonight is we want to see what that looks like on a graph. What are the limitations of Hooke's law? What does it say? And then how do we go about calculating this spring constant? Because this is a kind of regular exam question, especially towards the end of the paper. Alright, so onwards and upwards, we want to imagine ourselves in some form of situation where we actually have to graph this out. So the experiment's pretty simple. What you have to do is you have to get yourself some form of mass or some form of stretching force. Usually it's a mass hanging from something, but it could be something pulling something else across a desk or anything along those lines. It's just a little bit easier. And what that does is that, say you have a spring or something like that, it's going to extend your spring, because your spring under normal circumstances is nice and tightly wound, okay, like this. Alright, now if you measure the length of your spring originally, this is called your original length, and sometimes has the kind of symbol L naught, your original length. Okay, then this here, if this is your first mass going on, this would be L1, where you measure the full length of the spring, and it's now your first length. Add another mass onto that, so we've got a little bit more drawing to do. Do that again, okay, and whoop, wrong line. And your spring's going to stretch out even further. So you end up with something out here. And let's imagine that we have a bigger mass on here, so let's put two of these over here. So put two of those on there, like that. Then this one is no prizes for guessing. We would measure the length of this, and then we would label that as L2. Okay, now at any time the extension x is equal to whatever length you have, so let's say it's L1, take away your original length, L0. The extension for the second one is equal to L2 minus L0. Okay, it's always the first one. Okay, it's always the original length you're taking away from your new length. That's really important. Lots of people make that mistake, right? And you need to get into your head, you're always taking away the original length. So it's a good idea when you're doing these experiments, get a measurement for L0, write that somewhere down, and then make sure you're taking that away from everything else. If you're drawing up a table for this experiment, because this is a prescribed practical, this is one of the ones that you can be asked to perform, you'll be looking at force here, measure in newtons. Note the forward slash here, the solidus, okay, that rather than brackets. Okay, so force is measured in newtons. Here we would have extended length or new length or just length of spring, and that's going to be measured in maybe centimeters, maybe millimeters. We'll get to that later. And then finally you'll have extension over here, and that's going to be measured in whatever the unit was that you measured the length in. Alright, so up somewhere else on your page you'll have a measurement of the original length, and you'll be able to fill that in. Okay, now this is important, the order, because this is good scientific principle, that as you read across a set of results, you should have an idea of the order in which the person actually performed the experiment. Okay, that you went and you got a force, you added that onto your spring, you then measured the length of the spring, you then calculated the extension. Alright, and I can see that because we read from left to right on here. Alright, so that's the experiment kind of set up, done. What do we get at the end of it? Well, we don't really actually care about the length of the spring. I don't want to fill the whole table, but that'll do. We don't really care about the length of the spring here. Right, what we care about is the force and the extension, because Hooke's law only deals with force and extension. But we need to get the length in order to get there. Right. What we then do is we get a graph grid, and we draw this out on our graph grid. So let's give me a nice red line. Okay, so we draw a y-axis, we draw an x-axis. Now, under normal circumstances, what you would do is you'd do something like you'd put force across the bottom and extension up the side, because force is your independent variable here. It's the thing you're changing. But in this case, we're not going to. In this case, we're going to put force up the side, okay, because we have half an eye as to what we want to do with that later. And then we're going to put extension across the bottom. And again, I'm going to pretend that we did it in centimeters, but it doesn't really matter in the slightest. Okay, now what we're expecting to get here is we're expecting to get a straight line through the origin graph. Okay, something that looks a little bit like this. So when we plot our points in, we'll get a little x here, and make sure they're x's. When you're little small x's, nice and neat, so that the examiner can see them, that they don't get wiped out by the line that you draw later. They scan well if we're doing electronic marking. Alright, now why do we think there's going to be a straight line through the origin? Well, it's because of this equation. Because if we think about how this equation works, if we have force on the y-axis, and we have extension on the x-axis, and we have an equal sign in between, and k is some form of constant, then this follows the form y equals mx, where the thing you plot on the y-axis against the thing you plot on the x-axis has some form of constant. And that constant is the gradient of your graph. And because k is a constant and isn't changing, then the gradient of your graph shouldn't change. The slope of your graph should not change. If the slope of your graph does not change, it's a straight line. There's no extra plus or minus bit over here, so we're expecting this to go through 0. This is because when the force equals 0, it doesn't really matter what k is, the extension will have to be 0 in order to make 0 on both sides. Alright, so we're expecting a straight line through the origin. And this is what we get. When we perform the experiment, we do get a straight line through the origin, and this is wonderful. Alright, we can then use our rules of graphs, and if you're not a big fan of graphs, go back to one of my streams earlier on in the year to get how to deal with graphs, how to calculate gradients, how to deal with y equals mx plus c, all that stuff. What we can then do is we can get the gradient of this graph by doing rise over run, or delta y over delta x, or whatever way you want to do it. Now, in these ones, it's a really good idea to have your first point down here. Okay, to get a gradient, you need to pick 2 points on your line. So there's a point there, and here's a point here. Now we've got x's at those points, but I didn't have to use those. I could have used this point, okay, and drawn a triangle with that. We want a nice big triangle that takes up more than half of my graph. All right, this bit here is how high the graph rises up. So this is called the rise, and this bit over here is called the run. If you really like being technical about things, and believe me, I do, this is called delta y, because delta means changing, and across here, this is delta x, the change in x. Alright, so our gradient is equal to, just going to move this graph out of the way a bit so that we've got space to have a proper chat with you. So just slide this across here slightly. Okay, the gradient of my graph is going to equal the value of my rise divided by the value of my run. So this will be rise over run. And this forms a fraction. You pop that into your calculator and you just get that sorted out in a proper line. There we go. Okay, or if you want to write it mathematically and you want to show off a bit, m equals, because m is the symbol for gradient, is equal to delta y divided by delta x. Okay, your change in y divided by your change in x. Alright, easy peasy. So let's just do a little sample calculation here. So let's say this was 2, 4, 6, and then 8 and 10. And across the bottom here we start at 0. This starts at 0 as well. Doesn't have to, but it's a really good idea to have 0, 0, because you're expecting your line to go through 0, 0. And let's say this value over here is something like 8. Okay? So my rise would go from 0 up to 10, my run will go from 0 across to 8. Or my change in y is 10, my change in x is 8. So m equals 10, my rise, divided by 8, which is my run. Alright, and that then gives us, pop that into your calculator, that's going to give me 1.25. Okay, that's my gradient. And we'll come back to it later, it's my spring constant as well, because my value for my spring constant, k, is equal to whatever the value for the gradient of this graph is. Okay, provided I've got force up the side and extension across the bottom, my gradient is the spring constant. Now remember what we said, that the unit for the spring constant was changeable. It would depend on what you did. Okay, so the rise here is not 10. It's actually 10 newtons. Okay, because the unit up the side is newtons. So we've got 10 newtons up the side, and across the bottom we have 8 centimeters. So whilst we did do the 10 divided by 8, we didn't actually deal with the newtons divided by centimeters bit. Nor do we intend to. We actually intend to just leave it there as newtons divided by centimeters. That's how units are made. This slash here means divide by. We call it per when we're saying it out loud. So this is newtons per centimeter. All right, and this is basically Hooke's law. Hooke's law says that that the force and the extension are proportional to each other, or the extension of an elastic object is directly proportional to the force that's applied to it. But there's a little bit that comes onto that, okay, and it's a little bit that everybody forgets about, and it's until the limit of proportionality is reached. Right, and this goes into any definition that you have of Hooke's law. Because this graph does this up to here, but there does come a point where this stops working and your graph starts to become not linear. It starts to curve. Okay, and this is because that as you stretch a spring more and more and more, or anything, then what you end up with is you end up with the material stopping looking like a spring. Like a spring's made of wire. It's wound round and round and round. If I stretch it far enough with enough force, it goes back to being a wire and ceases to be a spring. When it does that, it stops following the rules for elastic objects. And the point at which it stops doing that is called the limit of proportionality. And the limit of proportionality is, surprise, surprise, where the graph stops being proportional, which is where it stops being a straight line. Now you may have heard in class things about the elastic limit and the, up to the elastic limit. Do not refer to the elastic limit when talking about Hooke's law. Okay, this is something that's a little bit later on. Okay, the elastic limit for some materials is a little bit further on than the limit of proportionality, maybe around here. The elastic limit's where if you let all the force off it, it goes back to its original shape. Right? It's not the same place as the limit of proportionality, and therefore you shouldn't talk about it when you're talking about Hooke's law. You should talk about that the extension is directly proportional to the force applied until the limit of proportionality is reached. And that's all there is to it. Okay? That's all there is to it. If you're ever asked to calculate a value for the spring constant, you need to draw a graph of force against extension, plot the graph, and find the gradient. The y-intercept is always going to be 0, so don't worry too much about that. Okay? Happy. So we're halfway, so we want to switch now to the idea of pressure. Alright, so let's imagine that we have a desk or something like that there. Nice solid desk form here. Get ourselves a little other brown going on there. There we go. Right, and onto that desk I'm going to place a little metal block. Okay, so I need to get a little metal colour for that. Let's get that a little bit of greyness going on. If we had time to play around, we'd probably play around with the gradient fill, but we're not going to tonight. Alright, so I've got that sitting on the desk, and what I'm going to do is I'm going to apply a large, sharp downward force to it. F. Okay. Now, if you were to be asked what is likely to happen in this situation, the likelihood is that nothing's going to happen here. Okay, the thing's sitting on a desk, assuming the desk is reasonably secure, then this is just going to go, alright, fine, I'm just being pushed at a desk. That's how it works. Grand. Okay, you're being pushed down into a desk, nothing even remotely interesting has happened. Even if this is quite a large force, that's probably true. Like, think about if you put a book on a desk and you leaned your whole weight onto it. It's not going anywhere. It's not doing anything. You'd be extremely surprised if the book sank into the desk. You'd start to worry that your desk wasn't made of wood, or that you were in some way in an alternate universe, and that the matrix was real, something like that. But let's just change the shape of that ever so slightly. Let's make our little metal object, and let's give it a little head like that, but this time we stick a little triangular end to it like this, spin it round like that, and attach it like that. Okay, so I'm going to fill these in, just give you a bit of an idea, give it a little line colour like that, so it's not nice, that's better. Okay, so having a look at that, immediately we see that this is a different game altogether. If I apply, once again, a large value of force to this, you would be very surprised if this thing didn't end up travelling through the desk. And this should represent a problem in your brain, because as far as the physics that you know so far is concerned, the force affects the acceleration, it affects the movement of the object. So why does this object move and this one, or this one sits still and this one is driven into the desk. And let's not assume that it's a thing to do with mass. Let's assume that this object here is just as heavy as this object here. So this is quite a heavy, like little metal nail or something like that there, and this is quite a light, hollowed out box. Right, so what's actually happening here is that the force that you're applying in this situation is spread, and it's spread over this kind of area here. Whereas the force that you're applying here ends up concentrated at a tiny point here. And this idea that when you have forces concentrated at a point that they can puncture through things, that they have a different effect on them, this effect is pressure. When you're put under pressure by your teachers, that is that they are applying a degree of force, they are applying a degree of like stress to you, but at a very specific point. If you really want to put pressure on somebody, you find their weak point and you focus right in on it. You don't just broadly wander about chatting to them. All right. This is because the actual ability to drive through something depends on two things. It depends on the force that you apply and the area over which it is applied. Okay, these are two things. Right? And this is the idea of pressure. And the equation for pressure is simply those two things. It's pressure equals the force applied, or just force, divided by the area over which it's applied. Force divided by. And these two things are divided. That making the area smaller increases the pressure. Okay, this is the idea. If somebody steps on you, then you get stamped on your foot. It's not a big deal, but if somebody rather gravitationally challenged, shall we say, steps on you with a stiletto heel, that hurts a lot. So that's grand. Morgan, the discovery of pressure, named after Pascal, but we'll come to that in the unit. And Spock doing the pressure point thing, that's sci-fi, but there is a point in your neck that's really, really sore if you grab somebody there, so I think it probably came from that. I'm not sure on that one. Okay, now force, as always, because Newton was a pretty self-indulgent guy, that's going to be measured in newtons. Area, on the other hand, in this case, can be measured in a variety of things. It can be measured in meters squared, centimeters squared, or millimeters squared. If you were super high scale, you could even do it in kilometers squared, though that's not going to come up in a GCSE situation. Right. So again, we're going to have to deal with our units in the same way that we dealt with our units in the last one. Okay? That we have to do the calculation and then we'll sort the units out thereafter. Okay? Now, graphing wise, this is kind of straightforward. That if you keep, now we've got three variables here, so to make a fair test, we would only change one at a time. So if we were measuring pressure, and we would put it in the y-axis because it's by itself. Okay, so if we were measuring pressure up the side and we were measuring force across the bottom, we would have to keep the area the same. So pressure against force for the same area, these two things are directly proportional to them. As you increase the pressure, you increase the force, but more importantly, if you double the force, you double the pressure. Right? That's not interesting. I honestly couldn't see you getting asked a question about that. There are so many other better situations where you can be asked about direct proportional relationships. The reason I bring it up is that there's another graph that's much more interesting, which is if you plot pressure up the side, again as you would because it's by itself and it should be the y-axis thing, and you plot area across the bottom, and of course you would have to keep the force the same, so you would always apply the same force, so force is constant, then what you end up with is called an inverse proportional relationship, because as you double the area you actually halve the pressure. And if we plot some points in this tends to go like this. You start up with a reasonably small area and a high pressure, but by doubling the area you actually halve the pressure, and then we double the area again, so we come out over here, you would half it again, and if we double the area, so we come across the same amount, we would half again, and then half again in each step, and you end up with this kind of graph here, which is a downward sweeping curve. Now I'm doing this with a mouse, so this is going to look utter garbage, but you'll do a nice smooth curve in your exam. Right, but you'll end up with this curve downwards, like this, that actually doesn't meet the x-axis ever, so we'll get rid of that. Okay. This is an inverse proportional relationship, and we can tell it by, if we take some values here, if you double one thing, so you double the area across the bottom, so pick two numbers like 10 and 20, you will actually find the pressure halves. This is called inverse proportion. Okay, that doubling one thing halves the other. This doesn't occur too much in GCSE Physics. You get the occasional one here and there, you get a few more things later on, but this is important. Okay, you've seen it in forces already with F equals ma, that the acceleration is proportional to the force and inversely proportional to the mass. This is another one. And if I was an examiner, would set this as a question to really, really, really sort out who knows what they're talking about. All right? Now, again, the questions are pretty straightforward. What you end up with is you end up with little 3D diagrams. So let's get ourselves like this type of thing here, and drawing a 3D box. Going to be fun, but we'll have a go at it anyway. Boop, 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 boop. Grab that, and then draw this. This is like the fastest 3D box ever. Please, no judgment. Right? Yeah, it's not too bad. Seen worse. Blind man never see it. Right, let's put it onto an object. Should fill that in, but I'm not going to. Alright, and what you'll end up with is a question like this. So a box of mass 5 kilograms and sides as shown is placed on the ground. Find the pressure. Okay, so this is kind of the multi-part question. Okay, and then you have some measurements in here. You have a measurement here, you'll have a measurement here, and I would definitely have this measurement here in for you as well. So let's put some numbers in here. Let's say this is 20 millimeters. Let's say this is 80 millimeters. This is severely not to scale, and let's say then that this is 130 millimeters up. All right. So we want to find pressure. So we know that the equation for pressure is force divided by area. We're going to shorten that a little bit. So P equals F over A. Pressure is force divided by area. Oh, wrong line. And then we just pop our numbers in. But we don't have any numbers. Okay, what we've got from our question is that we have the mass is equal to 5 kilograms. And we have a series of measurements here. Okay, so we definitely don't know the area. The area is unknown, and we definitely don't know the force. So we're in Snookersville, population snooker people. But we're clever, and we remember our stuff from weight. Okay, that we know that the force that's acting down on this object, because there's nothing else pushing it, is the weight of this object, and it acts directly downwards. So we're in business. Hopefully we remember that the weight is equal to the mass of the object in kilograms times the acceleration due to gravity on planet Earth, which is 10. So W equals 5 multiplied by 10. So the weight of this object is 50 newtons. Alright, cool. So we've got this. Now that's the weight, but the weight is a force because it's 50 newtons. There's no other forces acting. So this becomes 50. And it's newtons. We'll keep an eye on that. The area is the area in contact with the actual material you're looking at, which is the base area of this material. And the base area of this material then we have to go and calculate. So area equals length times width. So the area is equal to 20 multiplied by 80, giving us an area equal to, I need to move this little box out of the way. Oh, we do spell length correctly as well. Okay, so the area is equal to 20 times 80, so that's 1600 millimeters squared. And I have no desire to change this into meters squared or anything like that. I'm just going to leave it exactly where it is. It's going to become an awkward calculation later on where I need to grab a calculator, but that's alright. This equals, if I'm not asked to do anything fancy, don't do anything fancy. 50 over 1600. And we get the line in for that. Draw that out. And that then equals, that's going to be 5 over 160. That's not something you're doing in your head. So we'll just grab the calculator here from the side. Bring that onto the screen. There it is. So we're going to do 50 divided by 1600. Gives me 0. Whoop, wrong one, so we need to do that calculation again. 0.03125, so 0.03125. And again, we need a unit for this. Right, so the unit comes from the numbers you put in. That was 50 newtons divided by millimeters squared. So this is, we didn't do the newtons divided by millimeters squared. We didn't intend to, because we're going to leave it as newtons per millimeter squared. Okay, nothing to it at all. Pressure. What pressure? The only exception here is that there's a little bit of a convention. All right, that if you have your force is always going to be in newtons. So force in newtons. Now we play if games. If area is centimeters squared, then pressure is going to be in newtons per centimeter squared. Right. Easy peasy. I'm going to copy this line a couple of times. If the area is in millimeters squared, we're going to have pressure in newtons per millimeter squared. Once again, so far so good. If the area is in meters squared, you would expect that this would be newtons per meter squared, but it's not. This is incorrect. It's bad form. Not mathematically incorrect, it's mathematically spot on, but we don't use newtons per meter squared. We use a different unit. We call this the Pascal, PA. Right. Once again, if you discover something, you get to name it. So therefore, newtons per meter squared is given as the Pascal. All right. Now, as you get further on in physics, you get to do things like conservation of pressure, which is really good fun. It's how all hydraulic systems work. And if you're interested in this type of stuff, like how do you use braking systems, how do you use liquid to move stuff, this is the basic equation that you use. You just realize that if you've got a completely filled system of something like water that's incompressible, if you push one end of it, it pushes the other end. But actually, it's not the force that's transferred, it's the pressure. And you can do really cool stuff with that. But I'm afraid that's all we've got time for this evening. That was a quick whistle-stop tour of this. We're finished up now for Christmas, so we will be back again in the new year with some more stuff for Year 11 Physics. If you have anything that you'd like to suggest, anything you'd like me to do, anything that wasn't clear on the channel, please add a comment below. I'm trying to make this channel a little bit better, but hopefully it's and I will take feedback. Okay, I will take feedback. Get better. Like, I understand that, but if you can be specific, I would really appreciate it. Also, if you could like and subscribe, that helps this video get to more and more people, so I'd appreciate that. But all that's left to be said is happy holidays, happy Christmas, whatever it is that you're celebrating over the next month or so, and don't forget, everybody, physics rocks. It's true.